thank you very much for having me. I wish I could join in person, but unfortunately travel policies these days are still unpredictable. Okay, so I'd like to tell you a bit about the process of how we go from photon counts in a telescope to cosmology constraints and what synergies can really do to improve that situation and lead to optimal constraints. With that, let me just start with a preview of cosmology analysis in about 2025, because every cosmology talk needs a pie chart. And I think that cosmology analysis at that point will consist of about 5% parameters, which we know very well. Those are our lambda CDM or extended lambda CDM parameters. And then the remaining 95% of our parameters will be related to systematics. These come in two flavors: known unknowns, that is systematics that we already know about, and where we can now do our homework to maximize the constraining power of future analyses. And then also unknown unknowns that will really surprise us during the first pass data analysis, and where we will have to rely on synergies with other measurements to make progress. So let's get started. I will mostly give an outlook towards work with the Rubin Observatory, Roman Space Telescope, and in the same generation also Euclid, which have a photometric imaging component that in the case of these future experiments will image of order 30 to 50 galaxies per square arc minute over a few thousand to around 20,000 square degrees on sky. That's the future that we're preparing for. Of course, we will not be ready to just get to our desks and analyze tens of billions of galaxies. Instead, we have been building up for these analyses for a long time, especially in weak lensing. This started with a generation of surveys in the early 2000s, CFHT lens, Cosmos, and Deep Lens survey. With still very small areas and different strategies in terms of survey depths that really taught us how to do cosmic shear analyses. And right now we are in the rich era of three collaborations and friendly competition: the kilodegree survey, like energy survey, and Hypers and Prime Cam, really pushing forward these photometric like energy analyses. And that's what we need to build on to then optimize the science return of Rubin, Roman, and Euclid. So I'll start out with a brief description of what's currently going on, and then focus on synergies for the future later. But to get started, let's just briefly agree what we're measuring. In order to constrain dark energy, these imaging surveys mainly look at cosmic structure formation, where the basic idea is that gravity pulls things together and drives structure formation, while dark energy pulls things apart and slows structure formation. This is a measurement that's highly complementary to expansion rate measurements. And on linear scales, we can make good progress using perturbation theory. However, to capture most of the signal to noise, we'll have to turn to numerical simulations that will then predict the non-linear evolution of the dark matter distribution as a function of time, and for specific types of cosmologies that we can easily simulate. So, of course, you've all seen movies of this formation of cosmic filaments. The problem, though, is that, of course, the dark matter distribution is not directly observable. Instead, we have to turn to different traces of structure formation. So we will observe galaxy positions and shapes and colors, CMB and temperature and polarization, and probably many other wavelengths. And the question then is, how do we compare these observations to our theory predictions, which, if we go to simulation route, start out with a cosmological model and parameters, predict the dark matter distribution, and then still basically all of astrophysics has to happen to turn these predictions to maps or summary statistics for galaxies, light, and baryons. And we have to agree how to do this comparison. While there are many different ways of comparing theory to data, in this talk I'll focus on summary statistics, where we will condense these catalogs of billions of galaxies into measurements of the two-point correlation function, galaxy clusters, voids, three-point correlation functions, and potentially others as we get ready for more and more complex analyses. So the workhorse of most of these analyses is the two-point correlation function, that is the excess probability of finding galaxy pairs, over a random distribution as a function of separation. So we literally count galaxy pairs as a function of separation. And if we approximately know the redshifts or 3D distances, and if we have a working model for the relation between galaxy density and dark matter density, that is galaxy bias, then this measurement is easily related to the matter power spectrum, shown here at a few different cosmic times, from redshift 3 to 1 to today. And that matter power spectrum, of course, then includes a wealth of information that is linear growth here on large physical scales. Baryonic acoustic oscillations are imprinted here in the intermediate regime. And then there's an enormous amount of information at high K or small physical scales in nonlinear structure. A complementary measurement is galaxy clusters, where we set out to identify the biggest associations of galaxies or overdensities in the universe today. In the case of an imaging survey, that means that we will aim to identify which of these red galaxies here belong to a cluster. And then we have to figure out how that relates to the underlying halo mass function, which again is a probe of distribution of peaks in the early universe, volume evolution and structure growth. In order to do that step, we need a relation between the observed mass proxy, in this case galaxy counts, and the true halo mass. It's then called the mass observer relation, and is one of the key systematics in these analyses. The next tracer that I still want to introduce is weak gravitational lensing, where we're here looking at the coherent distortion of galaxy shapes by the tidal field of large-scale structure, so that in a highly exaggerated way, the background galaxies will align tangentially with filaments of intervening dark matter along the line of sight. Of course, in reality, this effect is much weaker than shown in the cartoon here. And our background galaxies have nearly random orientations. We do this measurement at signal to noise of about 20 per galaxy. So that's very different than looking at the ellipticity of a cyan sharply delineated ellipse against a background. That means we have to average over many galaxies, assuming random intrinsic orientations, and measure the shapes of these. That is a very complicated measurement. Fortunately, nature comes with a very convenient cross-check. Namely, we can measure the same gravitational lensing effect. In this case, imprinted is the deflection of the primary CMB anisotropies. Where in that case, that means that we reconstruct the intervening dark matter field now from the non-Gaussianity of the CMB anisotropies. This is a completely different measurement compared to the galaxy-based weak lensing, but still measures, of course, this exactly same physical effect. So this is an important cross-check, or also a synergy between different surveys that we can use to really make sure that we have our systematics under control. Now, of course, the best constraints will be obtained by combining all these different cosmological probes, which in previous iterations looked like, okay, we have, say, supernovae here, cosmic microwave background, and BUOs, which are all independent probes, so that we can go ahead and multiply the posteriors. However, if we want to combine these different traces of structure growth, and maybe also from the same survey that is with correlated systematics, then we cannot just multiply at the posterior level, but have to embark on fully integrated joint likelihood analyses, accounting for all the underlying correlations. That means that a lot of complications come in. If we just write this down as a simple Bayesian inference, we start out asking what parameters do we want to constrain, which combinations of data vectors can we measure, and also can we model all of these for our parameters of interest. If, for example, we wanted to constrain a particular modified gravity model that we can only, for which we can only do predictions in the linear regime, then cluster counts and cluster mass calibration in the highly nonlinear regime probably should not be part of our data vector. We will need cosmology priors, obviously, which can still lead to heated discussions, but let's just assume this is given for now. Then we will need a likelihood function, which so far is typically modeled as a Poisson for number counts and approximate Gaussian for two-point correlation functions. But clearly improvements on this will be needed for stage 4 surveys. We need a model for our measured data that includes consistent modeling of all observables, including dependence on all cosmology and nuisance parameters. And that will be the main focus of this talk. We will also need a joint covariance, and that is a large and complicated non-block diagonal matrix. But I've learned that meta 4-point functions don't really make for good talk topics. So ask me afterwards if you want to know more. And then the art in these analyses will largely be in the systematic parameters. These will clearly outnumber our cosmology parameters. So it means we need to parameterize and prioritize in order to finish our Rubin analysis in finite time. And their external synergies at different wavelengths, as well as simulations, will be crucially important to validate our modeling. And I'll give you a small flavor of this in my talk now. So we've often said that the era of precision cosmology is coming, and that will naturally happen as we move to bigger surveys, that is, smaller statistical error bars. So as survey size increases, statistical error bars shrink, and we obtain measurements with higher precision. However, that is not sufficient. In addition to precision, we will also need accuracy. We do want to, in the end, an estimate of the actual cosmological parameters, not just some unaccounted for systematics. And this comes at the cost of more complex analysis. So to get ready for that, we do have to talk about systematics, because excellent statistics will always mean that we're systematics limited, which is a challenge, but also an opportunity, because that really means that at this point we are person power and creativity limited. It is relatively easy to come up with a large list of systematics and nuisance parameters. The science then is in figuring out how to prioritize these and do these analyses in finite time. As a quick example, I polled the different dark energy survey working groups in 2013 before we had data, what their key systematics were. The answers are not surprising. Things like a galaxy bias, galaxy luminosity function, the cluster mass observable relation, shear calibration, photometric redshift uncertainties, and so on. But the shocking answer was that we were expecting of order 500 to 1,000 parameters at that point. That is clearly not feasible. So at that point, we have to start to prioritize and figure out which part of the data we really want to use. And I'll give you a quick worked example from DS next, before then talking about synergies of Rubin. So let's briefly get on the same page what I mean here by systematics and the impact on analyses. It's like a 2-minute start out with a theorist dreamland. We have a systematic 3D survey. Somehow we know what the underlying true parameters are, carry out our analyses, and find unbiased constraints with small error bars. If we had now ignored a systematic effect, then our analysis would have incurred a bias in the inferred parameters. In this case, we realize and say, there's a systematic missing. Let's put in a model. And then we marginalize over additional systematic parameters. At that point, we remove the parameter bias, but at the cost of increased uncertainty. We can then do this exercise for several different systematics already in preparation for our data analysis and figure out which ones lead to the largest degradation. Those are then our priority for obtaining better priors. That is, we can use synergies, say, with other wavelengths, or also calibration from simulations to improve our prior on these nuisance parameters and regain some of the constraining power that had been lost in marginalization before. Of course, the world and all our models will not be perfect. So in the end, we will probably end up with some small residual parameter bias and increased uncertainty. And then the art is to find a constructive way to speedy publication in these situations. Let me briefly give you one example of systematics in a 3x2 point analysis. That is the DES year 3 analysis, which used about 100 million galaxies for lensing measurements. That sounds like a lot, but it really is just a small stepping stone for getting ready to analyze billions of galaxies that will certainly come to our hard drives very soon from Rubin Observatory. So in this weak lensing cross LSS analysis, we have about 100 million source galaxies, which we split in 4 redshift bins, measure their shapes, and do weak lensing measurements. So then we have the lensing, cross-lensing autocorrelation, that is cosmic shear, shape autocorrelation, I mean. And we have about 10 million galaxies with relatively well-known redshifts in the foreground. These are split tomographically in 6 different redshift bins. For these, we measure galaxy clustering, and it is a position-position autocorrelation. And then we also do tomographic measurement of foreground galaxy position, background galaxy shape, that is galaxy-galaxy lensing. This is a massive analysis, and the full path going from pixel level data in terms of wide field images and point function modeling all the way to the 3x2 point cosmology is described in 30 papers that present a lot of algorithmic and modeling improvements in all analysis stages. So I will not go into these into details of these today, just to give you a flavor of the complexity that we already need to analyze 100 million galaxies. So you can imagine all the preparatory work and methods favorites that will be needed for Rubin analysis. On the topic of this talk, let me just briefly summarize the systematics model, which we confine to a linear bias of the foreground galaxies per redshift bin, magnification bias, again, per redshift bin, a simple intrinsic alignment model, and then, again, the simplest possible parameterizations for photometric redshift uncertainties for both galaxy populations per tomographic bin, as well as simple multiplicative shear calibration uncertainties for the weak lensing measurement per source redshift bin. This list is, of course, known to be incomplete. They are known but unaccounted for systematics, and we need to make sure that these don't bias our analysis. We do so by removing contaminated data points. That is, we throw out most of our signal to noise. For example, our baseline systematics model here does not include baryonic effects, which are known to have an outsized effect on the small-scale matter power spectrum. So remove all data points that where we expect significant contamination from baryons. And while we use galaxy bias that is piecewise constant in redshift, we of course don't claim that this choice of parameterization is some universal truth. So we also have to verify that these parameterizations are sufficiently flexible given our expected constraining power. And the answers that we come to for the DES-3 analysis, of course, are specific to that analysis. These do not carry over to Rubin analysis. We have to go through this validation work and enhanced modeling for each successive analysis. Let's cut to the result. Here are cosmology constraints from that DES-3 analysis, showing you 2 splits of our data, cosmic shear shown in blue, and in orange, a combination of galaxy clustering and galaxy-galaxy lensing. These are marginalized over 4, these constraints here on omega m and S8, so the clustering amplitude, are marginalized over 4 cosmology parameters, and all the systematic parameters that I just told you on the previous slide. So you can see that we get consistent cosmology from weak lensing and clustering and configuration space, at which point we are then allowed to combine these 2 splits of our data into the joint 3x2 point results shown in black. Now, in the context of external data, I'm repeating the DES results here in black, and then in green, that's the Planck results reanalyzed in the DES parameter space, as well as other low redshift probes of from BUO, redshift space distortions, and supernovae. And you can see that these are quite consistent. Specifically, we find consistent results between these low redshift probes and Planck at 0.9 sigma or P of 0.34. Of course, you can also see that the overlap between these contours is not perfect. So we want to do better. That means we need to observe more galaxies, combine more probes, and achieve better systematics control. And that's exactly our work plan, getting towards Rubin analysis. In terms of combining more probes, I very briefly want to highlight a paper led by Gretchen Chunhao, where we extend this 3x2-point analysis to now also include cluster number counts and the large-scale cross-correlation between cluster density, delta C, galaxy density, and reglensing. These large-scale 2-point correlations then allow us to constrain the mass-observer relation. That means cluster masses from large-scale clustering. This analysis has been extensively validated on DES-like mock catalogs. And in the end, we find cosmology constraints that are consistent with other DES probes. The aspect of this analysis that I want to highlight is that it unlocks constraining power from number counts. So we had added to the DES 3x2-point analysis shown in black here, cluster number counts, N, as well as several other large-scale 2-point statistics. If we remove the number counts and only look at large-scale clustering, cluster galaxy clustering, cluster lensing, that is basically we use galaxy cluster as an additional tracer for clustering, we obtain these green contours. So the information gain clearly is not in these large-scale 2-point statistics by themselves. Rather, the impressive gain comes if we then also add cluster number counts. Those are the red contours. So that is the potential gain from the qualitatively different cosmological information in the cluster mass function. Of course, we can only obtain this if our calibration of the mass-observer relation is accurate. And the plot here on the right, again, the red arrow shows you the expected gain in constraining power now on dark energy equation of state parameters. If we go from the fairly standard 3x2-point analysis shown in green to one that includes cluster number counts and cluster mass calibration. Of course, there's a lot of homework to do to be able to really realize this potential gain. Now back to other systematics and how much we can hope to gain from systematics control, which then of course also means synergies with other surveys or other probes. Here's a plot by Anthony Lewis, which I think is one of the most insightful plots about the DES-1 analysis. Gray shows the standard analysis. Then in red, all the systematics parameters are fixed to the best fit values and not marginalized. While that's not practical in practice, this of course illustrates the potential gain if the current systematics model could be fully constrained from external data. Then in blue also, now this analysis further removes all the scale cuts. So all the data points that we had removed due to nonlinear contamination are now included using just the same model. It is not expected that this contour would end up being consistent with the standard analysis. And clearly modeling these scales requires new systematic parameterizations, but it gives you an upper limit of how much we could gain from all this additional signal to noise, if we can figure out systematics models from other data sets. So let me just give you one quick example for that. And that is now the effect of baryonic effects on reglensing measurements. In our standard DES analysis, all the data points with the gray background are removed because we were not confident enough in the modeling of baryonic effects on these scales. In a very nice paper by postdoc Hongjin Huang, she reanalyzes the DES data, now including all reglensing measurements down to the left limit of this plot and accounting for baryonic contamination. So what we do here is that we build a principal component model for the effect of baryons on the matter power spectrum. This plot here shows the matter power spectrum of a hydro simulation compared to the gravity only simulation for a large range of current hydro simulations, Massive Black, Eagle, Horizon AGN, LSST, and different flavors of Bahamas and Cosmo Owls. We hope that this range of simulations then brackets whatever feedback strengths there might be in the real universe, so that if we build a PCA interpolating between all these scenarios, then we can marginalize out the effect of baryons on our observables. And that's what's shown here. First, in orange, we repeat the DSU1 baseline analysis with conservative scale cuts. The blue contours then include all scales, but model baryonic effects with a PCA and a completely non-informative prior. So you can see at that point, the constraints are slightly weaker than the conservative scale cut analysis without baryons. However, if we include a weakly informative prior on our baryon parameters, that is then the gray analysis, that shows a gain of about 20% in constraining power. And by informative prior, I now mean that we know from X-ray observations that, for example, the original illustrious feedback model was too aggressive. And we basically rule out that scenario based on synergies with external data. We can, of course, also turn this analysis around and plot our posterior from this small-scale weak lensing analysis on the first baryonic principal component, which we named Q1. And the various vertical lines here then show where the different simulations fall. And basically, the Cosmo Owls AGN scenario with AGN heating of 10 to the 8.7 Kelvin, clearly excessive, basically is inconsistent with this data, even with conservative priors. And similarly, illustrious and the next highest Cosmo Owls AGN temperature are also in the tails of this distribution. The synergy and way forward here now is to use more external data, say small-scale TSC measurements, to really constrain and self-calibrate baryonic feedback parameters, and then in turn put more and more constraining priors on our weak lensing analysis and enhance the constraining power. And that's one of the main ways forward for utilizing small-scale information in weak lensing. So with these practical examples, let's talk about how to optimize the science return from Rubin Observatory and contemporaries then. And even though these will be long duration surveys, the future is starting very soon. Rubin Observatory will start commissioning very soon, and the year one analysis, which will already, of course, already cover the full survey area at a fraction of the depths, will already be a very exciting data set for cosmology. So let's get ready. Here's just a view from the summit from earlier this year, show you that yes, construction is basically done. The observatory is getting ready for commissioning, and as cosmologists, we should really get ready for the data analysis. Here is now a forecast of what we consider basically LSST desk baseline analyses in our science requirements document, which is available in the archive, and importantly includes links to data products and Fisher matrices for giant forecasts carried out by the collaboration. And these are the first forecasts since the LSST Science book in 2009. So these are based on a much more mature survey and analysis assumption, and also enhanced understanding of systematics. These joint forecasts include cross-correlations, the statistical and systematical ones in the covariance and shared systematics. For the systematics, we consider two classes: self-calibrated ones, that is galaxy bias, intrinsic alignments, and the cluster mass observable relation. And those are that are externally calibrated, that is photometric redshifts, shear calibration, and photometric calibration. And then in this plot, you can see the constraining power of the different probes in the Rubin analysis. clusters, strong lensing, supernovae, and streakers 2-point, and also the much stronger joint constraints. For completeness, I just briefly want to highlight a nice paper by the Euclid collaboration doing similar cosmological forecasts. Again, joint Fisher forecasts from spectroscopic clustering, photometric clustering, and weak lensing. And this paper includes an extensive validation of forecasting codes. That was really impressive to me. And importantly, the forecasts include different scenarios, both optimistic and pessimistic for the different systematics. So that's another very useful resource to really look at how important systematics are for these forecasts. These are the baseline analyses, of course, until the survey really starts and we agree on everything, there's still some optimization to do in terms of survey strategy and everything. In the past, that was a very simple task. We could just say that higher number density of galaxies is always better. The next step, if we vary both number density and area, then at least for like energy science cases, that is fairly late time universe. If we have to pick, then we should probably increase area first before increasing depths. But it is still a relatively simple problem. This is statistical error bars only though. If we now move to systematics dominated stage 4 forecasts, then we really have to talk about how well we control different systematics and what that means for cosmology constraints. As one simple example here, I want to come back to galaxy bias, which is the relation between a galaxy population and matter distribution. If we take the conservative view of signaling we can only do this on large scales, then we end up with a family of forecasts like this blue, black, and red contours using slightly different cutoff scales, showing the constraining power for combining with lensing and galaxies is frequent super analysis using large-scale galaxy bias only. If, however, we are ambitious enough to say that we will be able to also utilize small-scale galaxy clustering and sufficiently marginalize over the associated uncertainties, in this case, quite flexible HOD model, then the gain in constraining power may be transformative, as shown by the green contours here. This is comparable to having more than 2 full skies of Rubin Observatory, which clearly is very futuristic. That will require very advanced intergalactic space travel. So clearly learning how to model and use the constraining power in small-scale galaxy clustering is quite realistic compared to getting 2 full skies of Rubin data. And thus, I think, a very worthwhile endeavor. And you can see that this has a dramatic impact on the constraining power, which means that realistically, our survey optimization then will become much more complicated. The availability of external data sets and synergies with those will be a key component, for example, informing how well we can calibrate our cluster mass observer relation, and then all kinds of other modeling concerns that will really determine how good our cosmology constraints can be. This is a very complicated space. One dimension is clear though, each of these is quite expensive. So we will have to prioritize among them. Let me just briefly give one more worked example of stage 4 streakers 2-point forecasts, especially Rubin and Roman, where the details really matter. So here you can see the comparison between a forecast without any systematics as the inner contour, and then including marginalization over linear galaxy bias, photometric redshift uncertainties, and shear calibration. And clearly, that is a factor 2 or more in constraining power already. So the assumptions on this really matter. I want to go in some more detail here now on the forecasting for the Roman high latitude survey, where the important point is that the observing strategy for Roman Space Telescope is not yet defined. And community input is still being solicited to define a mission that benefits all science cases. Rubin also has no expandables that limit the survey strategy or survey duration to 5 years. Propellant is there for at least 10 years of observations, and there are no active cryogens. This chart here on the right shows you some simulation of the observing timeline, showing how the observing timeline might be split as a function of time between microlensing in purple, supernovae in blue, the galactic plane in green, and then those small red parts of this graph, that is the high latitude survey imaging component, where I will be talking about the optimization. The previous plot was the current nominal Rubin baseline scenario. And we have gone through very detailed forecasting, starting from the exposure time calculator for realistic survey depth and area, going through the Kendall's Roman catalog to get a redshift distribution for a lensing and clustering sample and galaxy clusters. And then in addition to 3x2 we also combine cluster number counts, cluster weak lensing, spectroscopic galaxy clustering in supernovae 1a, accounting for the full non-Gaussian multiprobe covariance between all these measurements. And in a full simulated likelihood analysis that marginalizes over more than 80 systematics parameters, we then obtain constraints for all these different individual and combined probes, which look like this. So that is our baseline forecasts for the Roman reference survey based on marginalization over more than 80 systematics. And in this plot, you can see how we go from weak lensing to the 3x2 analysis, then 3x2 plus clusters, cluster number counts and lensing, including also RSD and BEO, and finding supernovae 1a for the for our current best prediction for the joint Roman combined probes analysis. Another hypothetical scenario that I want to highlight here is the Roman-wide survey. Where it's important to realize that Roman also has a W band, which you can basically think of as a very broadband light bucket. So because of the high throughput of this W band, we would be able to cover basically all of LST's area and obtain space quality shape measurements for more than 95% of the LST year 10 gold sample within just 5 months. If we wanted to go to 99% completeness, that would be about a survey time of about 1.2 years. And our idea now is that we would combine W-band survey for space-based shapes with Rubin imaging for photometry and see how well we can do. So the comparison here is in blue, our high latitude reference survey, the baseline forecast that I just showed you before. And then in red are the baseline LST year 10 3x2 forecasts. And the much smaller black area, that is the HLS wide survey, combining space-based shapes with Rubin photometry for this joint ground space-based 3x2 analysis. So I think this would be an excellent synergy between these two contemporary surveys. So far, that's only weak lensing and galaxy clustering, not including clusters of spectroscopic redshifts. So there's, of course, much more optimization one could do. And we find that Roman-wide plus Rubin would be an improvement in about 2.4 over the Rubin-only case. Of course, in the end, reality will be different than these idealized forecasts. And we will have imperfect prioritizations, end up with residual parameter biases at the cost of increased uncertainty. And likely we will be in a situation like this, where we do our first pass analysis of the individual probes of one of these future surveys, and then end up in a situation like this, where we have to ask, okay, have we detected new physics or unknown systematics? And that's really where external synergies will come in. Internally, we have, of course, the chance to check whether our contours will get closer together if we change our scale cuts, for example, exclude more nonlinear scales, or whether our results depend on the galaxy cluster selection. or we can start to synergize with external data. That is, we calibrate with more accurate measurements. We can follow up on photometric redshifts with spectroscopic redshifts. We can improve over optical clusters using low scatter cluster mass proxies like TSZ. We can compare our ground-based galaxy shapes with space-based imaging, showing here a comparison between Subaru, which is our closest guest right now for LSST-like imaging quality, with space-based shape measurements. And this comparison of the ground-based galaxy identification with space-based shows you how important galaxy blends will be for future analyses. So clearly, each of these more accurate calibrations can lead to tremendous gains, but they're all potentially very expensive. Compared to this object-by-object calibration, we also have the opportunity to correlate with other surveys. That is, we compare the predicted cross-correlations to the actual measurements. And if we find consistency, showing that we were not plagued by an unknown systematic, then we can use these cross-correlations to constrain uncorrelated systematics. The worked example that I want to highlight here is a nice paper led by Manu Shan, where we looked at how well we can constrain the shear calibration uncertainty, that is the uncertainty in lensing measurements from cross-correlations with CMB-S4 lensing. And the red contour here, or the red line, is the most important. It is combining LSST with the full LSST 3x2 analysis with CMB-S4 lensing. And we can see that we will constrain our shear calibration uncertainties by comparing galaxy-based lensing and CMB lensing to better than the requirement, especially for high redshift galaxies, where traditional techniques for calibrating these shape measurement uncertainties are really difficult because galaxies get more and more irregular as we go to higher redshift. And with that, I'd like to conclude. That is, we're entering the decade of very large galaxy surveys. And we know that most cosmological constraints from these will be systematics limited. That means we need accurate systematic standardizations and priors. And to get there, we will have to heavily rely on synergies. First, between different probes within the same survey. And also then, as a next step, between different surveys. This joint analysis will allow us to first identify and understand systematic effects, and then afterwards synergize to maximize concerning power in a full joint analysis. However, the most important takeaway point here is that these precision cosmology analyses will require collaboration across surveys and wavelengths, and we have to plan in advance for analysis frameworks that allow us to work together and combine data 5 years from now. Thank you.
Thank you very much, Elisabeth, for a very nice talk. Do we have any questions from the audience? Okay, we have one.
Thank you. Hello. Yeah, thank you very much. Coming to your last point, so in this talk you showed us how to combine all these observations and what's going to happen in the future. But could you frame also this in some of the parameters that precision cosmology may want to constrain better in the future, like neutrino masses? Are you gonna, with all the surveys, close the window? Or, I mean, something about the tensions in the data is, I mean, after 5 years, are we gonna have a kind of definite answer to sigma 8 or H0? I mean, one of these things, or is still far in the future, the answer to this?
So, I mean, each of these analyses has to be optimized for a particular science case. When I, for example, started with my cartoon of systematics, saying that we'll have to basically go through the potential impact of different systematics and how much they help with, how much they can degrade, or after calibration from external data, improve constraining power. That is completely analysis and parameter specific. Our optimization will be different for neutrino mass, where we really need to control small scale physics compared to dark energy parameters. So I don't think there is a one fits all answer. But of course, we should make sure that our preparatory work makes sure that we are set up for not just dark energy parameters, but also S8 neutrino mass and so on. However, each of these require dedicated forecasts and assessment of which analyses, which systematics we can control. So I don't have a one fits all answer.
Thank you.
Do we have any other question from Zoom or Slack? I have a question. Oh, we have a raised hand. David. David, please.
Hi, can you hear me?
Yes.
Okay, hi, Elisabeth. So yeah, you finished by saying that a lot of this stuff is going to require a lot of collaboration between different collaborations. So which aspect of the analysis do you think is more critical in kind of establishing those collaborations? Is it the modeling or simulations or what is it? Yeah.
So I would think that making sure that at the end we have likelihoods that can talk to each other across different surveys will be critically important. If that's not the case, then being able to share the rest doesn't really bring us forward. Of course, a joint pixel level analysis will have benefits for some of these probes as well, and being able to share simulations can also allow a lot of prevent wasting a lot of computing time. But I think one of the real main bottlenecks will be being sure that we will be set up with a likelihood framework where we can actually interpret cross correlations. But I hope you'll provide a different perspective on that and maybe also some more details on Saturday. Look forward to your talk on that.
Thank you. I guess a follow-up question, if I can. I don't know if there's others waiting. Is so you've shown that there's a lot of work that needs to be done in order to keep systematics under control in the usual n times 2-point analysis, and it's kind of daunting how much of that we're going to have to do for Rubin. But so do you think it would be worth trying to prioritize as well other kinds of analysis in terms of higher order statistics or you know, any kind of higher order stuff that is not just looking at 2-point functions? Or is you know, is that going to be even harder, so we shouldn't even try at this point because we have too much work to do?
I absolutely think we should try. Okay. I'm not sure if it's if it has reached maturity to really make it our baseline analysis. But it would be sad if in the end we only had the baseline analysis.
Cool, thank you. Yes, thanks.
Okay, let's thank again Elisabeth for a very nice talk.